Hello students, welcome back to my 12th lecture on basic maths. In our previous lecture, we have started with the topic relations where A and B to be non-empty sets. A relation R from A to B is a subset of A cross B. That is, a relation R is from A to B. And we also studied domain and range of a relation and inverse relation. So in today's session we will see some different types of relations like identity relation, null relation, universal relation, reflexive relation, and so on. So let's get started. What do you mean by an identity relation? Let A be a non-empty set. The relation I of A defined by IA, that is the notation here we will denote it by I of A is equals to within a set in a pair of order A comma A, both are same here, therefore it is an identity where A belongs to set A, called the identity relation on A. Similarly, null relation where A be a non-empty set and null set is a subset of A cross A. Hence, here see null set is denoted by the symbol 0 and 1 hash inside this. Is a relation on A. This relation is called as a null relation on set A. Similarly, for universal relation, let A be a non-empty set, then A cross A is a proper subset of A cross A. In universal set, students, all the elements will be included in one single set only, that is here it is denoted by A, and hence A into A is a relation on set A only. This relation is called as a universal relation on A. Next type is reflexive relation. A relation R on a non-empty set A is called a reflexive relation if both the elements must be same. Reflexive, how we will see your own image, you will get your own image in front of the mirror, same only. Reflect is nothing but here in the maths reflexive. If A comma A belongs to relation R for all A belongs to R. For example, here see A is given with 3 elements ABC. Then we can frame a relation as R1, that is equals to A and A, same elements in a single pair, ordered pair, and B comma B. Similarly, in second relation we can write all the same elements in an ordered pair. Hence such sets are called as a reflexive relations on relation A, on a set A. Then second one, symmetric relation. A relation R on a non-empty set A is called a symmetric relation if AB belongs to R and also it implies BA belongs to R. In the previous example, we have seen the same elements in an ordered pair. In symmetric relation, we will see the reverse, inverse relation of an ordered pair included in the set R. So that is called as a symmetric relation. See, for example, A is given with 5 elements 1, 2, 3, 4, 5. Then relation R1 can be written as 2, 3 and its inverse relation is 3, 2. 3, 4 and its inverse relation is 4, 3. If such ordered pairs in a relation will be there, then such sets are called as a symmetric relation. Similarly, in the same example, second relation, we can write it as 1 5 will be 5 1, 2 5 and 5 2. Reverse of the first ordered pair must be there in a set to make a symmetric relation. Next, one more important, that is transitive relation. A relation R on a non-empty set A is called as a transitive relation if AB and BC belongs to set R, then it implies A to C, A to B, B to C, and one more relation from the same sets is equals to A to C. If it is there in the set R, then such relation is called as a transitive relation. For example, let R be a relation on the set of naturals defined by is a factor of, that is x r y is defined by x is a factor of y and y r z is defined by y is a factor of z. Hence, from these two we can imply x r z, that is x is a factor of z. That means relation x to y, y to z, then also it will become a relation from x to z. Next one, equivalence relation. A relation R on a non-empty set A is called an equivalence relation if it is reflexive, symmetric and transitive. Students, please do remember this definition for exam point of view. So, we will prove this with one example. So, consider on a set L of straight lines in a plane. So, our first reflexive relation will be line L1 is parallel to itself. Yes or no, students? Two lines you take down. So, L1 and main line is L. One big line you have, that is capital L. So, L1 is parallel to itself is a reflexive relation. And second one, consider two lines from the set of L of straight lines in a plane. So, L1 is parallel to L2, then obviously L2 is also parallel to L1. If both the lines are parallel to each other, then it makes a symmetric relation. L1, L2 belongs to relation R, implies L2, L1 relation belongs to R. Hence, R is a symmetric relation. And for transitive, if a line L1 is parallel to L2 and L2 is parallel to L3, then obviously L1 is parallel to L3. So, it will be written like this: L1, L2 in one ordered pair, L2, L3 belongs to relation R, which implies L1, L3 belongs to R. Therefore, R is transitive. Since R is reflexive, symmetric and transitive, it is an equivalence relation. In equivalence relation, it has to satisfy all these three conditions. It must be reflexive, symmetric as well as transitive. Next one, antisymmetric relation. A relation R on a non-empty set A is called as antisymmetric relation if AB and BA belongs to R. Means both inverse and as well as a relation of AB and its inverse must belongs to relation R. Then we can say A is equals to B. For example, consider the relation R defined by is less than or equal to on set of integers. Then if xy belongs to R such that x is less than or equal to y and y is less than or equal to x. If both the conditions satisfy, then we can say x is equals to y. Therefore, XR is an anti-symmetric relation. Now, through the examples, you will understand better way. First example, if A is equals to 1, 2, 3, 4, 5 are the elements of set A and set B contain its elements 1, 2, 3, 4 and R is a relation from A to B defined by R is equals to the ordered pair XY such that Y is equals to 2x plus 1. Now find R. So here see, you need to find the value of R. So by substituting the value of x, by taking 1 as x as 1 and y as 2x plus 1. That is, I will take the value of x as 1, any value you can take. Then substitute in value of y. Here we have taken x value as 1. So 2 into 1 is 1 plus 1. That will be equals to 3. Here based on this condition we have to find the value of r. On substituting the value of x is equals to 1, you get y value is equals to 3. This is the relation defined on the condition. Similarly, for second example, R is relation on the set of natural numbers n standing for x is related to y. That is, if x is equals to 3y, find R. So here they have clearly said it is the set of natural numbers. So you can take x value as 1, 2, 3, 4 and you will get the value of y also. So if you consider here x value as 3, okay, x value is 3, then that is equals to 3 is equals to 3 into y. To get y value, you divide it both the sides by 3. 3 by 3 is 1. Then you will get y value as 1 here. So you do one thing, otherwise to make your work more easy, take y value as only 1, 2, 3, 4. Okay. So if you take y value 1, then you will get x value as 3 ones are 3. Okay. If you take y value only as 2, then you will get x value is equals to 3 2s are 6. And y value if you take 3, then you get x value is equals to 3 into 3 is 9 and so on. So you can write a relation like this. Hope you are understanding, students. Next example, third one. Given A is equals to 1, 2, 4, B is equals to 2, 3, 5 and R1, R2 are relations from A to B by is less than, find R. Here see, same one relation only you have to find, that is R, but the condition is here is less than, means first relation should be less than the second one. Like that you have to frame an ordered pair. So that is equals to R is equals to 1 is less than 2. Make a relation like this. First domain should be lesser than the range. Okay, 1, 2. First element should be less than the second one. Keep it in mind. 1, 2, 1, 3, 1, 5, 2, 3, 2, 5, 4, 5. Okay, first number must be less than the second one. Like that you have to write an ordered pair. Next example. This is also very important example, students. A relation R is defined on the set of integers by R is equals to x, y such that x minus y is a multiple of a non-zero integer 5. show that R is an equivalence relation on Z. So since they have asked us to show that it is an equivalence relation, it has to satisfy the three conditions, that is reflexive, symmetric and transitive. So given here is x is a factor of x only, that is here in the condition R, x minus y is a multiple of non-zero integer 5 is given. So since in reflexive relation the same image, that is range and domain must be same, that is x minus x is a multiple if 5 for all x belongs to integer. So 5 minus, if you take x and x minus x, you will get 0. 0 is a multiple of 5. Why? Because there is an integer. Integer contain all non-negative integers, positive integers including 0. Hence R is reflexive. For symmetric condition, x is a factor of y. That means x minus y is a multiple of 5. Then 5 divides x minus y. If x minus y is a multiple of 5, then obviously 5 divides x minus y. That is, see here, x minus y can be interchanged in symmetric. How? X comma y should be written in the inverse relation as y minus y and x. Therefore, interchange here in the next step, that is minus of y minus x. Why I have written minus here outside the bracket? Because to retain x minus y in the same position. Just reverse it, minus y must be there, then minus minus will be plus x. So that is nothing but y minus x. Therefore, yx also belongs to relation R. R is a symmetric. X and y belongs to xy belongs to relation R. It is an integer, and also yx belongs to relation R. Therefore, it is an symmetric relation. Similarly, for the third condition, for transitive relation, xy belongs to R, yz belongs to R, then we can write it as y divides x minus y, and also 5 divides y minus z. Now add the denominators, that is x minus y plus y minus z. Then y are similar, they will get cancelled. You get 5 divides x minus z. Simplification. Then xz also belongs to relation R. Therefore, R is transitive. Since R is reflexive, symmetric and transitive, then R is an equivalence relation. It has to satisfy all these conditions. Then it is said to be an equivalence relation. Students, can you try this? Exercise 2.4. For 1 mark questions, such types of questions you will get. Given S is equals to 1, 2, 3, 4. State which of the following is a relation on S. Relation on S. Here see, first one is a relation on X. Yes. R1 is equals to 1, 2, 2, 0. Since 0 is not there in S, so first one is not a relation on S. 0 is not there only in the set S. Therefore, first one R1 is not a set. A relation on S. Similarly, go for R2. 1, 3, 4, 2, 2, 4, 1, 4. Just try yourself. 1, 2, 3, 1, 3, 4, 2, 2, 4, 1, 4. Means these all elements must be there in set S. Other than 1, 2, 3, 4, if 0 will be there or 5 will be there, then it will be excluded. It will be not a relation. So second one is a relation. Third one is also a relation. See, what about R4? There is a 0, there is a 5 also. So clearly from set yes, we cannot make a relation R4. So R4 is not a relation on yes. Okay students. Next. Second one is a homework for you. Just try yourself and send me the answers. Third one also. Try third one. Try 2 marks questions also. Try yourself first. 3 marks questions will be like this. List all the relations on the set A, B. Seventh one. All the relations on the set from A, B means which all you will get. See, from A to A cross A will be AA, AB, BA, BB. Okay. From this relation A on A, we can make many relations again. Okay. So this is an answer for 3 marks question. Okay. Again, from this AA, you can make proper subsets. In the previous class, in proper subsets, how you used to write power set? Use that one and try to solve the 7th one for 3 marks. Then define equivalence relation. Give one example. So other than line, you can go for triangle, you can go for circle to prove an equivalence relation. Write down the definition first with one example. Okay. Next, 9th one. If A is given 4, 5, 6, 7, R1 is given 4, 4, 5, 6, 6, 7, 7, 7. Represent R1 by diagram. So here 4 and 4 will form a loop. 4 is relation to itself only, 4 to 4. Loop it will form. Draw circle 4 to 4 only. Loop how we will draw? Write down 4, then draw a circle over there. Then 5 to 6, write down 5 and 6 on a line, then make one arrow mark. Similarly from 6 to 7, 6 to 7, draw one arrow mark, and again 7 to 7, write down a loop. Okay. Next concept is functions. So here set X and Y be non-empty sets, then a subset of X into Y is called as a function if the following conditions holds good. That is, for each X belongs to capital X, there exists a unique Y belongs to capital Y, such that both small x and small y should be belongs to a function. Then second condition, elements of X should not be repeated. That means first pre-image, that is first set should not be repeated again. See, conditions here are as a note. If x1 y1 belongs to function f, then x y2 belongs to f, then y1 is equals to y2. These all notes we will prove with the diagram now in the next class. Y belongs to y is called as the image of the element x belongs to x, and x is called the pre-image of y belongs to y. Means we will draw one set for x, one circle or set for y. First one is called as a pre-image, second one is called as its image. The set x is called as the domain of the function f, and the set y is called the range of the function f. See here, in this you will clear your difficulties in the note in the previous slide. Example, consider A is equals to 1, 2, 3 and B is equals to A, B, C. Let F. In the previous slide, we have done with relation. From the sets only we have created a relation. Here also same case. Two sets will be given. From that you have to frame a function F. So F is equals to 1A, 2B, 3C are ordered pair respectively. This can be shown in the diagram given below. So here two diagrams are given. In the first set of A, first diagram, that is called as a pre-image, and B diagram is called as a image. You can simply draw it like an oval shape. So that is, A contains the numbers 1, 2, 3, write down inside the oval shape, and write down elements of B in the second diagram, A, B, C. Now clearly they have taken an ordered pair from 1 to A, that is mark from 1 to A, 2 to B, 3 to C. Then write down function A to B. Write one arrow mark and write down F over there. A is a function to B. So here F of 1 we can write it as A. F of 2 is equals to B. F of 3 is equals to C. In all the representations, every element of A is associated with a unique element of B, and there is no element of set B which is not mapped onto any element of A. All the three elements of A and all the three elements of B are mapped to each other. Second example, A is equals to 2, 3, 4, B is equals to 4, 5. Now F is given, that is 2 to 4, 2, 5, 3, 5, 4, 5. Since here, see here the diagrams, two ordered pairs in F have the same first component. Compare first example and second example. See, in second example, F have the same first component. Therefore, it is not a function. Okay, students. See in the diagram, oval A contains 3 elements. Oval B contains 2 elements, 4 and 6, 4 and 5. So 2 is making a maps with 4 as well as with 5. So your 2 is repeated 2 times. Therefore, this is not holds good according to the definition. X should not be repeated. A should not be repeated. The same terms of the image, pre-image, should not be repeated by definition. Therefore, it is not a function. Next concept, domain, codomain and range of a function. Let F from A to B, that is F is a function or mapping from A to B. The set A is called domain of F and the set B is called the codomain of F. The set consisting of all images is called as a range of F, which symbolically written as F of A. That is F is equals to 1A, 2B, 3C, 4D. So domain here as the first element of ordered pair, that is 1, 2, 3, 4. And range here as range of F is equals to F of A is equals to A, B, C, D. And codomain here are the second elements of an ordered pair. Note here that F of A is a proper subset of B Every function is a relation, but the converse is not true. Converse holds does not holds good. So students, till here I conclude. In our next class, we will meet with the different types of functions. Thank you.